Today's lesson is all about radicals and rational exponents. And rational exponents just mean exponents that are fractions. So we'll talk about that more in a second, but I'm just going to kind of leave a note up at the top here so it pops out to us. And then just remember it's of course a video, so you can pause it, rewind it, and rewatch any examples that you want. So this first section is called rational exponents, so like fraction exponents, and nth roots. Nth roots just mean like kind of like square roots, but they don't have to be a square root. They could be any type of root. So there's like square roots, cube roots, fourth roots, and so on. There can be any type of root, which is like a radical. So if you want to kind of pause the video and copy this down and kind of fill in as I go along, feel free to pause it here. If not, I'm going to zoom in and start in the upper left corner. Okay, so first thing, we can use a radical symbol, which looks like this, to represent square roots and other types of roots. So for example, the square root of 16 is 4, because if we were to take 4 and square it, it would be 4 times 4, which is 16. So square roots and like a squared exponent are inverses of each other. They have the opposite effect. So think of it as like one is going forward, one is going backwards. But there's not just square roots. For example, we can take the third root of a number, or you'll hear like the word cube, like kind of like a three-dimensional square. So a cubed root means we're looking for a number that like multiplied together 3 times to get the number inside the radical. So the cubed root of 64 would be 4, because if we were to take 4 to the third power, that would be 64, and that's 4 times 4 times 4. Okay, moving on to the next spot, so just one to the right. Rational exponents are exponents that are fractions. So these are just a few examples of rational exponents, but I know sometimes that just the vocab in math can kind of be like a barrier, but just try to get into the habit of when you see rational, think fraction. And they like kind of look like similar words, just some letters switched around, so hopefully that helps. But they mean essentially the same thing, especially when we're talking about exponents. Okay, so these are just a few examples of rational exponents. So I have x to the 1/2 power, it's a fraction, 27 to the 1/3 power, and 16 to the 1/4 power. So you'll see like some of them are written kind of like horizontally, like as if you were to type them. Some of them are vertical. There's no difference between the two. It's just kind of the way that they were typed in. Okay, moving down to the next box on the left, we're gonna go back to these like perfect squares and perfect cubes on the far right in a second. So each part of a radical has its own name. We're gonna label each part on this like fifth root of 32 kind of problem. Okay, so the first one, of course, is the radical. So it looks like this. It's that kind of like check mark symbol. So this is called a radical. And then the next one is, we're going to talk about this 5. The formal word for that is index. But you may hear me refer to that as root. Sometimes that feels a little bit more of like a natural word to call it, because if it's, 3 there, it would be a cubed root, or in this case, it's a fifth root. But root and index, those would have the same meaning. Index is a little bit more of like a formal definition. And then now inside of the radical, that number, that whole thing is called a radicand. So radicand. And that's the number inside. And then we would read this whole thing as the fifth root of 32. So you, like the little number tells you what type of root it is. And then of course the inside is like the number that we're trying to make it equal. So this problem in particular, it's asking you what number times itself 5 times, or what number to the 5th power would equal 32. So just off to the side somewhere, I'm gonna say like, okay, I'm gonna put a blank there. And then I'm going to raise that to the 5th power. and then that's going to equal 32, that would be like the answer to this problem. So if I take 2 and I raise it to the 5th power, that equals 32, because if I do, hold on, I write it, 2 times 2 times 2 times 2 times 2, this would be 4, this would be another 4 times 2, 4 times 4 is 16, times 2 is 32. So if I take 5 2's and multiply them together, I get 32. So that would mean the 5th root of 32 is 2. And not all of them will have like exact answers like that. Okay, moving on to the next part. It's really helpful to get comfortable changing between the forms. So between radical form, which radical form looks like this, to rational exponent form, which looks like this. So the first 3 boxes are done for you. So these 2 and then this one down here. Take a second, pause the video, and look to see if you can identify a pattern that is taking us from the radical form to the rational exponent form. So if I'm looking at this, I'm actually going to go to this box first. So if you notice, the index over here becomes the denominator over here, and then there's a 1 on top in the numerator. And then here, the index 4 becomes the denominator here. We don't have an index written here, but if there's no number there, it's a 2, and that's what the denominator is over here. And then all of the numerators are 1, so that stays the same on each one. So we can use that pattern to put the 5th root of x into rational exponent form. And then notice that the base stays the same, so x, 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 and so on. So it's going to be x, and then my index is 5, so that's going to go in the denominator, and then 1 in the numerator, so x to the 1/5 power. Okay, and then the next section says, starting right here, roots and radicals are inverse operations. That just means they undo each other. So kind of like how addition and subtraction undo each other, and multiplication and division undo each other, roots and radicals do the same thing. So I'm going to zoom in on my examples, starting with this square root of x squared, or sorry, square root of 7 squared. So I know if I don't see a number here, this is a square root. So if I have a radical that has an index of 2, it cancels out an exponent with an index of 2, and I would just be left with what was inside the radical, the radicand. So just 7. And then over here, same thing, the index and the exponent are the same. So I have a 4th root and a 4th power. So those undo each other, and I'm just left with the radicand, the number that is inside, so 5. I forgot to type my equal sign over here, but I have the 3rd root of 24 to the 3rd power, so my index matches the power it's being raised to, so those cancel each other out, and I'm just left with what was inside the radical, the radicand, so 24. And then notice this last one, it had parentheses, but it didn't really impact the way that we approached the problem. Okay, so a couple of key takeaways. So now going on to this box down here. It's really important to get comfortable with the terminology. So the index tells you how many numbers are being multiplied together to get the radicand. So that's the number inside the radical. I'm going to just make a note for both. So index, I'm going to say, is like the small number, like the little one that's into the upper left of the radical. And then the radicand is the number inside. So for example, if I had a problem that said the 4th root of 16, I would be looking for a number that would be raised to like the fourth power or multiplied by itself 4 times that equals 16. So that number would be 2. Because if I do 2 times 2 times 2 times 2, that would be 16. And then the second one down here where it says rational exponents or fraction exponents are the same thing as a radical. So going back to like this box, we could write it in either form, but they were the same. So if I had a radical, that was the same thing as having a fraction exponent. Or if I had a fraction exponent, that was the same thing as having a radical. So they're interchangeable, they're just in different forms. So for example, if I have like 25 to the 1/2 power, I can rewrite that in radical form, and that's a lot easier for me to figure out when it's in radical form personally. So remember the denominator was the index. So this becomes a square root of 25, which is just 5. Or like in this case, 27 to the 1/3. The denominator of the fraction was the same thing as the index. So it becomes the third root of 27, which is 3, because if I were to take 3 and raise it to the third power, I would get 27. Okay, the next thing I just want to touch on is this table up here with perfect squares and perfect cubes. It's really helpful if we can get kind of the first set of them, I guess, memorized. So by first set, I mean like this is from 1 through 10, the perfect squares and perfect cubes, because it's really helpful to be able to identify like what you can take the square root of or the cube root of without a calculator. So for example, like if I saw the cubed root of like 216, I would know it's 6 if I have an idea of what this table looks like, or I could at least kind of pull the table out and reflect back on it, so you could like save it in your notes, save it to your phone, whatever you want, so you can find it easily. And that'll just kind of make the problems go by a little bit quicker for you. So the next section goes with 2.2, or the 2.2 workbook, and it's changing from radical form to rational exponent form. And there is kind of a little pattern that you can follow. In your workbook, they use different variables in the pattern or the formula, but it's the same pattern. I just use variables that kind of connect a little bit more to what they represent, as opposed to just using like X and Y where they don't really like follow what they represent, I guess. So I'm going to zoom way in here. The left side is radical form, it has the radical. The right side is rational exponent form, it has that fraction exponent. So I use R, B, and E to represent base, root, and index. So for B, we call that the base. And then for R, I'm going to use the word root. Remember, index is the more formal, but root looks or works a little bit better here. And then for E, it's the exponent because it's being raised to that power. So B is the base, the number inside the radical. R is the root, like the index or the type of radical it is. And then this is a power that it's being raised to. And then once we change it to rational exponent form, I mean, burr is not a word, but I always read it that way, like B-E-R, burr. It's just easier to like remember the order of how things go. So my base stays the base of the exponent. And then the exponent from radical form becomes the numerator of the fraction, and then the root becomes the denominator of the fraction. Sorry if my audio just changed a little bit. Oops. Okay, so this is something I would write this down on like a sticky note. or just somewhere where it's like really easily accessible, where you can write it kind of big and then just have it next to you while you're working on all these types of problems, because it's not something that's super easy to remember right away, but it is a really important skill to have and to use to change between the two forms. Okay, so we're going to start now on the left side where it says change 11 raised to the 3/7 power to radical form. So we just want to go through and identify, okay, what is B, what is E, what is R? So B is 11. It's the base of the rational exponent. And for this problem, we're starting in rational exponent form. So we're actually starting on the right side of the formula, and then we're going to the left side to get it to radical form. So B is base, and then the E is the numerator of the fraction, and then the denominator of the fraction is R. So I'm going to take that B, E, and R, and I'm going to substitute it into this formula. So the B is what goes inside the radical, so my 11, and then the R is going to end up being my root, so that was the denominator of the fraction, the 7. And then the numerator of the fraction is my exponent, so I just put that as an exponent up here. And it can go inside parentheses, or you can leave the parentheses off. Technically, it can also go inside of the radical, but there's not a lot of problems where that's helpful. So I usually recommend putting it outside the radical, but just know it can go in either place. So it becomes the 7th root of 11 to the 3rd power. And then the next one, so starting right here, says change the 4th root of 13 to the 9th power to rational exponent form. So in this one, we're starting on the left side, it's in radical form, and then we're going to the right side in rational exponent form. So we want to go through, figure out what E, R, and B are. So B is the number inside the radical, R is the root, E is the exponent. And then I'm going to take that B, E, and R and substitute it into this. So B becomes the base of the exponential, so 13. And then the original exponent from the radical, that's what goes in the numerator of my rational exponent, so 9 goes on top. And then the root goes in the denominator of my new fraction, so over 4. So the 4th root of 13 to the 9th is 13 to the 9/4 power. Okay, and then the next one we're just evaluating. So that means kind of like find a final answer. So for example, if I gave you a problem that said evaluate the square root of 16, that would be 4. You're evaluating it, you're kind of finding a final value. Okay, so when I see fraction exponents, I don't like evaluating in them in that way. I feel like it's pretty confusing. I like to put them in radical form. So both of these are in rational exponent form. They're in this form right here. We're going to put them in radical form first before evaluating. So I'm going to zoom way in. We're just going to label each part. So when it's in rational exponent form, it's B to the E over R. And then when I put it in radical form, it becomes the R root. So in this case, it would be the 3rd root of B, so 64. And then that's raised to the E power, so E was 2, so squared. I think it's a lot easier if we take the root first before dealing with the exponent. The order doesn't technically matter here. You could use the exponent first, but that would give you like a really big number because it would be 64 squared. So I'm going to take the 3rd root of 64. That's like what number cubed equals 64? It's 4. And then that has to be squared. And then 4 squared is 16. So final answer is 16. This is where like if you don't like have all your squares and cubes memorized, having that table from the top of the notes like available is very helpful. So if I was wondering, okay, what is the 3rd root of 64? Since it's a 3rd root, I would look over at my perfect cubes until I got to 64. And then because so 3rd roots will go with perfect cubes and square roots will go with perfect squares. So because 4 cubed is 64, the cubed root of 64 would be 4. so that's where our 4 came from, and then you could even find 4 squared on the table if you wanted to, but if not, it's just 4 times 4, so 16. Okay, and then number 2, we're going to go about it the same way, just figure out what b, e, and r, and then switch them into radical form. So when it's in fraction exponent, rational exponent form, it's b to the e over r, and this would definitely be like a good time to pause and see if you can do it on your own, and then use the video to check your answer. And then once we put it in radical form, it's the r root, so the 5th root of b, so of 32, and then to the e power, so squared. So the 5th root of 32 is asking what number to the 5th power equals 32. We already kind of did this problem earlier in like the 2.1 section, but the 5th root of 32 is 2, because if you were to do 2 to the 5th power, that would equal 32. And sometimes you just kind of have to guess and check. So we took the 5th root of 32, that was 2, and then now we just need to copy over that squared. So 2 squared means 2 times 2, so 4. And then the next section is 2.3, it's simplifying radicals. There's 2 different methods of simplifying radicals. They're both mentioned in your workbook. You can decide between the 2, but there's definitely certain cases where one may be more appropriate than the other, and we'll talk about those after. So method 1, there's not really like a name for it. Method 2, you can see has a name, it's prime factorization. I like to think of method 1 as like breaking something down, but prime factorization, it kind of seems like breaking something down too, so I'm not sure what the name would be or what a good nickname would be. So I'm going to start with the square root of 50. So the square root of 50, or 50 itself, is not a perfect square. However, it can be simplified because it has a perfect square factor. So you can go back up to that list to see the perfect squares, but just as a reminder, perfect squares are like technically 1, but we'll start with 4, 9, 16, 25, and so on, all those numbers that you get from squaring other numbers. So if the number inside the radical, the radicand, has a perfect square factor, it can be simplified. So I know that 50 is 25 times 2, so I'm going to break it down into the square root of 25 times the square root of 2. And when you're like kind of multiplying numbers inside the radical, so I could technically rewrite this as like the square root of 25 times 2 all in one radical like that, but that means the same thing as this. You can, like, if you have numbers being multiplied inside a radical, you can separate them into different ones, and I feel like this second way makes a little bit more sense in my head once I go to simplify. So it's up to you, whatever you prefer. But now I can go ahead and take the square root of 25, that is 5. And then I have the square root of 2 that's being multiplied by it. You don't need to include the dot anymore like that. And then 2 does not have any perfect square factors because it's prime, so we're done simplifying there. So it would be 5 times the square root of 2. And then the next one, we're going to use the same method. This one's a little bit different because we have this number out in front though. So for 12, 12 does have a perfect square factor, so the square root of 12 can be simplified. 4 is a factor of 12. So I'm going to rewrite this. I'm going to try putting it all under one radical for right now, so it looks a little bit different than the last one, just so you guys have an example of both. So I have 3 times the square root of, I know I can break down 12 in different ways, like I can do 4 times 3, or like 2 times 6, but I'm focused on the perfect square factors, which 4 is the only perfect square factor of 12. So I'm going to break it down into 4 times 3, because 2 times 6 just really wouldn't do me any good. And then now I can go ahead and just take the square root of 4. When I take the square root of 4, it's going to come out and be multiplied by anything else that is in front of the radical. So it would be 3 out in front. And then when I take the square root of 4, that's 2, so it'd be times 2. And then I have my radical left over. I don't have the 4 inside anymore because I already simplified that. I took the square root of it. I just have that 3 left over. And then now I can go ahead and multiply these numbers in front. So 3 times 2 is 6, and then times the square root of 3. And you don't necessarily need to write this step if you just kind of recognize that, okay, so 4, the square root of 4 is 2, and then I'm going to multiply the 2 by the 3 to get 6 and just jump here. That's okay too. Okay, so the second method, and this is the last part of the notes, so it's called prime factorization, and it's when you make a factor tree and you find all the kind of common factors. So the difference between the two methods, method 1 is pretty quick and efficient if you know the factors of what's inside the radical. So like for 50, I knew I could do 2 times 25, and for 12, I knew I could do 4 times 3. I don't really know the factors of 252, so that would be kind of difficult for this one. It would take me a lot of time, so there is an alternative method. So what we're going to do is we're going to make a factor tree. So we can just kind of break it down from here, or if you wanted to do it off to the side, you could. But we want to find all the prime factors of 252. And when it's a number that you don't really know the factors of, you can always start with something small. So like 252 is even. So off to the side, I have my calculator. So I'm going to do 252 divided by 2, which is 126. So I'm going to do 2 times 126. And then I'm just going to keep going like this. We're not going to go any further than 2 because that's a prime number. So that one's stopped. But now I can break down 126. That's even also, so I'm going to do 126 divided by 2 again, which is 63, so it'd be 2 times 63. This 2 is prime, so we're done there. I can break down my 63 into like 7 times 9, and those aren't the only two combinations. You just have to pick two numbers that multiply, so I could have done, for 63, I could do like 3 times 21, but 7 times 9 was the first thing that popped into my head. And then 7 is prime, so we're done there. And I'm going to break my 9 down into 3 times 3, and those are both prime, so those are finished. Okay, so now when we use this method, we need to look for pairs of the same number on our like air quotes like leaves. So basically we're only looking at all of the prime numbers at the bottom of this factor tree. So only looking at those 2s, the 7 and the 3s. So when I look at that group, I need to find some pairs. So I have it's probably easier just to leave those highlighted. When I look at those, I have the 2, 2, 7, and the 3. So for my pairs, I have a pair of 2s, and then I have a pair of 3s. And any number that I have a pair of gets to come out of the radical. So I have a 2, I have a 3, and those both get to come out. So I'm actually going to backtrack a little bit. Your workbook goes into like more detail in these steps, so I don't want that to throw you off. So I'm just going to go ahead and rewrite all these numbers inside the radical, and then after we finish, I can show you a little bit of a shortcut. So I have 2 times 2 times 7 times 3 times 3. I just took all of like those light pink highlighted numbers and put them in the radical. And then 2 times 2 is 2 squared. And then times 7 times 3 squared. And we know that like a square root radical, this doesn't have a 2 here, but it's a square root. We know those kind of cancel out and undo with squared powers. So that means that we can take the square root of 2 squared and 3 squared, and those would get to come out of the radical. So it'd be 2 times 3 outside of the radical, and then that 7 is not being squared, so that one can't be simplified. And then now we just have to go ahead and multiply the 2 times 3, so it becomes 6 times the square root of 7. So final answer would be 6 times the square root of 7. And then kind of like the shortcut I was mentioning is each pair on the bottom of your factor tree, that represents a number that you get to pull out. So I get to pull out 1, 2, and I get to pull out 1, 3. So for every pair, you pull out one of those numbers. And then I take those two numbers, the 2 and the 3, and I would multiply them together to get 6. Or you can see they were out here out in front before. So the 2 comes out, the 3 comes out, multiply them together to get 6. And then any number that is not a part of a pair, so the 7, that's what stays inside the radical. Okay, this next one, so the square root of 504, same thing, like I can't really think of like the factors in my head that may be a perfect square, so I'm going to make a factor tree. This one is even as well, so I'm just going to go ahead and divide it by 2 and see what I'm left with. So I'll do 504 with a calculator is fine, divided by 2 is 252. If you don't like want to use a calculator, that's good mental math, so more power to you. So 252 now divided by 2 again, because it's even, is 126. Oh, is this the same number? Oops, okay, it'll still be a good example. So 252 divided by 2 is 126. And then 126 divided by 2, I'm going to keep breaking it down, is 63. So 2 times 63. And then 63 is 7 times 9. I'm going to pick a different combination though, just so we can kind of see how it doesn't matter if you pick 7 or 9 or a different combo. For 63, I'm going to pick 3 times 21. And then for 21, I'm going to pick 3 times 7. So just kind of comparing between the two trees on the last problem, we did 63 went to 7 and 9. But still from that 63 kind of like branch, I ended up with a 7, a 3, and a 3. And from here, the 63 branch, I went a different way. I picked 3 and 21, but I still got a 3, and a 7. So I still got the same numbers at the end. Okay, so now we have to figure out what pairs we have. So we're only looking at the prime numbers at the end, so all the ones that I highlighted in pink. And then we're specifically looking for pairs of 2. So I have a pair of 2s right here, or you could circle like these 2s, it doesn't really matter. So a pair of 2s right here, a pair of 3s right here. And then I'm gonna skip this like kind of long work and just show you the shortcut from the start here. Just know some of the workbooks in Canvas may ask you to show those in between steps, so they may want them. So I have a pair of 2s, so I can pull out a 2. I have a pair of 3s, I can pull out a 3. I'm gonna multiply those 2 together. Remember, the numbers that you have pairs of get to come out of the radical. So 2 times 3 is 6, and then anything that's left over that's not a part of a pair would have to stay inside. So I have a 2 and I have a 7 that were not a part of a pair, so I would multiply those back together. I'm going to put a little green multiplication symbol down there. So 2 times 7 is 14. So our final simplified form would be 6 times the square root of 14.